Good evening, friends, and particularly good morning to our speaker, Professor Vivek, Amin, and maybe good afternoon to people in Europe. Thank you very much for joining this webinar. So I'm really delighted to welcome Professor Vivek, Amin to this webinar series, and all of you for joining in, obviously. So on behalf of my WTS team, my co-convener, Dr. Rajbhushan Singh, and the team members, Puspendra, Ajhar, Shakti, and others, I express my sincere gratitude to Vivek for joining and kindly agreeing to give this lecture. I think Vivek is quite well known in the field of spintronics. He has given many invited talks recent times in many conferences. But just for the young students, I like to tell a few words about Vivek. So Vivek, Amin, is an assistant professor in the Department of Physics at Indiana University, Purdue University, Indianapolis, since last year. So he received his BS in electrical engineering from the University of Texas at Austin, and a PhD in physics from Texas A&M University. Prior to joining the Purdue, he worked as a postdoc and a research scientist with a joint position at the National Institute of Standards and Technology, that's known as NIST at Gettysburg, and the University of Maryland, College Park. Professor Vivek Amin uses computational and analytical methods to study electronic transport in condensed matter systems with focus on spintronics, quantum materials, and neuromorphic computing. So today you will be talking about the spin-orbital torque. So with this brief introduction, I again welcome all of you. I just like to mention that during the lecture, we don't take questions. So if you have a question, either you raise your hand or you write your question in the chat box. And then later on, we will take all the questions. Also, a small request that at the end of the lecture, before we take the questions, please switch on your video when I say, then we will take a group photo just for the our kind of souvenir. And then we will take the question answer. So with this, Vivek, it's all yours. Please start your lecture. Thank you so much.
All right, and thanks so much for having me. I'm very happy to virtually be here. Let me go ahead and share my screen. Please let me know if you can see the screen and you can see the animation. Is it coming yet?
Yes, it is coming very well.
Okay, great. All right, thank you. So again, I just want to thank the organizers for inviting me to tell you a little bit about the work that I've been doing over the past several years. So the title of this talk is Anatomy of Spin-Orbit Torque. And so, what I would like to do in this talk is introduce some of the traditional and sort of new mechanisms which underlie this very interesting and potentially very useful phenomena called spin-orbit torque. So let me start off with what I'd like you to take away from this talk. Spin-orbit torque is essentially a low power way to write magnetic memories. So over to the right of the screen, I'm showing a cartoon example of what a bit in a magnetic memory might look like. So you have this non-magnetic layer underneath a ferromagnetic layer. And if you turn on a voltage and run a current through this non-magnetic layer, through various interactions that involve spin-orbit coupling, you can then exert a torque on the magnetization and flip the magnetization. So if you store information in the direction of the magnetization, this is a way of writing the magnetic memories. And I will talk more about the physical processes underlying this going ahead. But there are several challenges facing spin-orbit torque. So first of all, it's not yet low power enough for widespread adoption. Experimental results are often inconsistent and theory does not match experiment. So it kind of sounds like maybe we don't know a lot about this, but actually we do. We're still just connecting the dots. So what I'm going to tell you about today is a prediction of new effects that hopefully will bring theory a little bit closer to experiment. So here's the outline of my talk. I'm going to start off with an introduction and then talk about the traditional model of spin-orbit torques. And I'll spend a bit of time on this because I know there are a lot of young researchers in the audience and maybe those who are not familiar with spin-orbit torque. So hopefully that will help catch you up a bit on what's been done so far. Then I will talk about novel mechanisms for spin-orbit torques that arise at the interface between materials, and then spin-orbit torques that arise in bulk magnetic layers. Okay, so first of all, why are we doing this? We're doing this because magnetic memories offer several advantages. They're non-volatile, meaning they retain their data when they're turned off, and they're radiation hard, which is important for space and medical applications. So again, to the right, I'm showing a very cartoony picture of what a magnetic memory might look like. We have these little nanodevices called magnetic tunnel junctions, which are arranged in some sort of crossbar architecture. And we have wires that are going through them to address them and potentially to read and write. So how do we store information in something like this? So the bits, again, comprise of magnetic tunnel junctions, which are two ferromagnetic layers and a tunnel barrier sandwiched in between. And the idea is that if the two magnetic layers have their magnetization pointing in the same direction, you could call that a 1. And if they're pointing anti-parallel, you could call that a 0. So that's a way of storing the information, but now you need to be able to do two things. You need to be able to read the information and write the information. So reading the information is relatively straightforward using an effect called the tunneling magnetoresistance. And all that says is that if I look at the electrical resistance for running a current out of plane, it's different for this configuration versus the anti-parallel configuration. And so I can read out the bit through the resistance. However, writing is an open challenge. I won't go through all of the methods of writing in the past, but I'll just say that the current state-of-the-art mechanism are spin torques. So right now you can buy commercial, there are commercially available MRAMs that use the so-called spin transfer torque in order to write memories. And essentially how that works is that you can use a small current to read, but if you just use a larger current, you can spin polarize the electrons in the bottom ferromagnetic layer. They will travel to the top ferromagnetic layer and transfer their angular momentum, thus switching the bit. But what I'm going to talk to you today is about SpinOrbit Torque, which you could think of as a next generation version of this effect. And what distinguishes SpinOrbit Torque from spin transfer torque is where the angular momentum is coming from. You're actually receiving angular momentum from the crystal itself, so from the atomic lattice. So how does this work? So over here, I've shown, again, this animation that has this magnetic tunnel junction with two ferromagnetic layers and a non-magnetic layer with appreciable spin-orbit coupling in the bottom. And so what happens if I run a current along the interface plane in the non-magnetic layer, the electrons start to scatter and separate based on their spin. And so what you end up getting is a spin current, right, or a flow of spin angular momentum in the direction that's transverse to where the current was going. And so when that spin angular momentum flows into the ferromagnetic layer, it interacts with the magnetization, is able to transfer the angular momentum. And that's how we can control the direction of the ferromagnetic layer. So unlike spin transfer torque, it's useful to think about this in terms of what the populations of spin are and what the reservoirs of angular momentum are. So with spin transfer torque, we have two reservoirs of angular momentum which are interacting with each other. So there's the magnetic order in the ferromagnetic layer, and then there are the carrier spins, and they're interacting via the exchange interaction. But when we go from spin transfer torque to SpinOrbit torque, we extend this interaction. So the carrier spins are now coupled to the orbital moments via spin-orbit coupling, and the orbital moments are coupled to the atomic lattice via the Coulomb potential. So through this extended interaction, you can actually steal angular momentum from the atomic lattice itself. So through the vibration of the crystal, and deliver it to the magnetic order using the carrier electrons as a mediator. So why do we care about this? Why do we want to do this? Well, the promise of SpinOrbit Torque is that this atomic lattice is essentially an infinite reservoir of angular momentum. So to understand that, we can think about an analogy with planets, for instance, and space travel. So what I'm showing in this animation here is the flight plan of Voyager 2 as it left Earth some 50 years ago and as it was exiting the solar system. So these dots are planets and the purple line is the path that the Voyager spacecraft took. And you can see that every time it passes by a planet, there's a kink in its orbit. And this is coming from the fact that this tiny little spacecraft is actually stealing angular momentum from the entire planet. But because the planet has so much angular momentum, it's a reservoir of angular momentum. The planet doesn't miss it. Nothing has changed for the planet. but with Voyager 2, there's a huge course correction. So what we're trying to do in SpinOrbit Torque is actually exactly like this, right? Instead of planets, we have these crystals, this atomic lattice, which is a virtually infinite reservoir of angular momentum. And the conduction electrons are kind of like our spacecraft. They can take angular momentum from that reservoir. And for our purposes, this reduces the electrical current needed from an external source, because we're just taking it from the device literally itself. So I've given a rosy picture of SpinOrbit Torque, and I don't know if there are any Star Wars fans in the audience, but there is a light and a dark side to SpinOrbit coupling. So the light side is that you're controlling magnetic order through spin currents and spin torques, and that arises from an angular momentum flow from the crystal to the electronic spins. But it goes both ways. So SpinOrbit coupling also leads to parasitic effects, such as spin relaxation or spin memory loss. So in this case, you have a reversed angular momentum flow where the electron spins just simply give their angular momentum back to the crystal. And so one of the open challenges with any sort of spin orbit coupling enabled device is how do you get more of the light side, so to speak, and less of the dark side. So I've been talking for a while about spin orbit coupling in this very general sense. So it's good to give a little bit of an overview of what it is for those of you who aren't familiar with the interaction. So SpinOrbit coupling is sort of exactly what it sounds like. It's an interaction between spin and orbital angular momentum, but how does it come about? So for that, we need to look back at the theory of relativity. So what relativity tells us is that the electric field and magnetic fields are related to each other in different reference frames. So for instance, if in one reference frame you see an electric field, in a moving reference frame, you'll see both an electric and a magnetic field. And there's a simple textbook formula that tells us how to relate those two. So what does this mean for spintronics, right? If I imagine an electron which is flowing through a crystal, right, and it scatters off of an impurity or an atom, something, it sees the electric field coming from the nucleus of that atom, but in its reference frame, in its moving reference frame, it also sees a magnetic field according to the theory of relativity. So if we're not too relativistic, then we can approximate the velocity as proportional to the momentum. And since the electric field is pointing radially outwards from the atom, we can say that that's proportional to r hat, or the radial vector. And this actually is the expression for angular momentum. So what that tells us is when electrons scatter through crystals, they see an effective magnetic field that is proportional to their angular momentum. We also know that if you have any sort of spin, it has an associated magnetic moment. And if you put a magnetic moment in a magnetic field, there's an energy cost depending on whether the moment is aligned or not aligned with the magnetic field. And since spin is proportional to the magnetic moment of the electron, and we just said that the magnetic field is proportional to the angular momentum, we see that spin and orbital angular momentum are coupled with each other. So the consequences of the spin-orbit interaction are vast throughout physics and chemistry. But in this case, what are we focusing on? So if we have an electron which is scattering off of a crystal and its spin is in one direction, there is an energy cost for it to scatter in certain directions. So for instance, this electron that has a spin down is going to want to take one orbital path as it scatters, because that's going to minimize its energy. Whereas if the spin is in the opposite direction, it's going to take a different direction. And so what happens then is as electrons flow through crystals and they see these impurities, they develop a spin current flowing transverse to the direction they were originally flowing, okay? So this spin-dependent scattering in this crystal is known as Mott scattering or skew scattering, and this is one way of creating so-called spin currents. So again, what does this have to do with magnetic memories and SpinOrbit Torque? To understand that, we should talk about the spin Hall effect. So in a non-magnetic material with appreciable spin-orbit coupling, if I turn on a voltage, so I get a current running through the material, as those electrons scatter with impurities inside the crystal, they will undergo those scattering processes. And what will happen, and this is guaranteed by symmetry, is that if we have the electric field in one direction, so the current flow in one direction, we get spin currents which are flowing perpendicular to the electric field, but the spin direction itself is perpendicular both through the flow and the electric field. So I know that's complicated, but essentially what we're saying is that the electric field, the spin flow, and the spin direction must be mutually orthogonal. So this is what's known as the spin Hall effect, and it arises by many mechanisms. One is an intrinsic mechanism, which is related to the Berry curvature of the band structure, of the material. The other are extrinsic mechanisms like what I just showed you with skew scattering, that type of scattering that separates the spins. And so how that then relates to SpinOrbit torque is that if you put this non-magnetic material underneath the ferromagnetic material, you get spins which are diverted into the ferromagnetic material. They precess incoherently around the magnetization and transfer the angular momentum to the magnetization, resulting in a torque. And so I'm not going to go over the origins of this formula. It's a well-known formula for spin transfer torque, but I would just ask you to maybe commit to memory that if you have a spin current flowing into a ferromagnetic material, if you just do the magnetization cross product with the magnetization cross with the incoming spin direction, you get the torque that results from, or at least the direction of the torque that results from the angular momentum transfer. And so what this sort of torque does is it damps the magnetization towards the direction of the incoming spins. However, there's also another mechanism which is associated with SpinOrbit torque. And in order to understand that, we can go back to our discussion about relativity. So if we think about the interface, right, between two materials, there's a difference in the work function between both materials, which leads to a very strong electric field pointing out of plane. Now, we know that when electrons are moving in an environment and they see an electric field, that also results in a magnetic field in their own reference frame, which again, via the analysis we showed before, gives us this effective magnetic field, right? Because the velocity is essentially proportional to the crystal momentum. And in this case, the electric field is pointing in the Z direction. So if I was to plot what this effective magnetic field looks like for the various directions an electron is traveling at the interface and solely at the interface, I get this diagram with these green arrows. All right. And so if all of these electron states are populated, then when you sum over all of this, the net spin is 0. All right. However, if you close the circuit and then run a charge current, say along the X direction, right, you imbalance the population of electrons so that there are more electrons flowing in this direction than the other direction. And what that does is that imbalances the spin as well. So you get a net spin when you sum over all of these effective magnetic fields times the occupation pointing in the Y direction, so perpendicular to the direction of transport. So this is known as the inverse galvanic effect or the Rashba-Edelstein effect. And essentially what it says is you turn on an in-plane electric field. At the interface, there comes a spin accumulation as a result. So now what does this mean for SpinOrbit torque? I turn on, I close this circuit, a spin accumulation develops at the interface, and as a result, I get the magnetization precessing around the spin accumulation, which looks like a torque with the magnetization dependence M cross S. So I see that there's a couple of questions in chat. Okay, these are just instructions, so I will move on. Okay, so let me then summarize these traditional SpinOrbit torques. So we have this spin Hall torque, which results from this bottom non-magnetic layer creating a spin current that flows into the ferromagnet and exerts a torque. That is one way of manipulating the magnetization of the ferromagnetic layer. Another mechanism is this Rashba-Edelstein torque. You turn on the electric field and you get a spin accumulation at the interface, and the magnetization precesses around that spin accumulation. And this creates two different directions of torque. The spin Hall torque damps you to the direction of the incoming spins. The Rashba-Edelstein torque creates a precession. So the open question then is, are these the only mechanisms, right? Are these the only ways that this can happen? And what are the consequences of SpinOrbit coupling in this device, right? Is it generative, the light side, or is it parasitic, the dark side? So here I'm now putting up, two papers, which I wrote with Mark Stiles in 2016, which essentially the goal was to analyze all the consequences of SpinOrbit coupling in a device like this, but using a very simple model. So that is now going to segue to the next part of the talk, which is what are the newer mechanisms of SpinOrbit torque that have been uncovered specifically at the interface between the non-magnet and ferromagnetic material. All right, so to understand this, why we would need to expand our picture, we have to go from 2 dimensions to 3 dimensions, right? So when I was talking about the Rashba-Edelstein or inverse galvanic effect, I was essentially describing an effect in which the electrons that are participating in this, are assumed to be, confined to the interface plane. But that's not how it works in a material, right? Electrons are constantly scattering off the interface plane. This is a three-dimensional problem, right? So before, with the Rashba-Edelstein effect, we assumed that there were some electrons that were basically confined to the interface plane. And if they were moving, say, in this direction given by this crystal momentum vector k, they saw this effective spin-orbit field u of k, and as a result, they were spin polarized along that direction. But the reality is more complicated than that, right? We have electrons which are flowing on either side of the interface plane, and some of those electrons are going to scatter off that plane. When they do, they're going to briefly interact with this spin-orbit field, and that's going to do two things. First of all, that's going to filter the incoming spins, right? So if I have an even amount of spin in one direction and opposite direction, and they scatter off the interface, what this effective magnetic field does is it creates a potential barrier that's spin dependent. And so what you have is some spins, like say these red spins, preferentially reflected, and other spins, say these blue spins, preferentially transmitted. And so basically the interface acts like a filter for spins, and that results in a net spin current flowing in the perpendicular direction. And so for lack of a better term, we call this spin-orbit filtering. But there's another thing that can happen as electrons flow through to the interface plane. If they're misaligned with this spin-orbit field, they can precess about it before scattering. And so we call that spin-orbit precession. It results in a rotation of the spin direction after scattering through the interface. So how does that create a torque? So let's go back to our model. If we have this non-magnetic layer, and now we're just focusing on one stream of electrons, which is scattering, off the interface plane. So I'll let the animation start over again. Hopefully there's not, a lag here. But as this current of unpolarized spin scatters off the interface, this spin orbit field they see at the interface filters the spins. And here I'm showing an extreme example where all the red spins get reflected and all the blue spins get transmitted. So if you watch closely what these blue spins are doing, they flow into the ferromagnetic region, they interact with the magnetization, and then they exert a spin orbit torque. However, if you look at the red spins, they reflect off the interface and create a spin current flowing down. So you have these two things that happen. You have a spin torque on the ferromagnetic layer, but you now also have a new source of spin currents that could be used potentially for other things. But I also talked about a spin orbit precession effect. So now if we consider, for instance, the electrons in the ferromagnetic layer, right, the majority carriers are not aligned with the magnetization, the minority carriers are aligned with the magnetization. When those carriers scatter off the interface, they see this spin orbit field, but they're not aligned with it, so they temporarily rotate around them. And as a result, you also get a torque on the ferromagnetic layer and a spin current generated in the non-magnetic layer, but it has a different dependence on magnetization. Here it's M cross S. Okay, so I've talked about these, using a very simplistic model. Essentially it's like a free electron gas with a delta function scattering potential. And just to show that essentially, these things, quantitatively will happen. But what about a more qualitative, estimate of these effects? So for that, we have to turn to first principles transport calculations. So here, what you're looking at are transport calculations in a cobalt copper interface. So the cobalt is ferromagnetic, the copper is non-magnetic, and actually copper doesn't have very strong spin-orbit coupling relative to platinum. So this is a material where you want to expect very strong spin current generation in the bulk, right? So what we have here is an electric field, which is pointing along the interface plane. So here that's into the screen. And for the cobalt, we have the magnetization also pointing into the screen. So we have a flow of electrons into the screen. And what we're going to do here is calculate all of the scattering that occurs at the interface, and then specifically look at the out of plane spin currents that result from that. And so that's what I'm plotting on these two plots over here. So the blue curves represent the spin currents of this orientation, where the flow is out of plane, but the spin is along the y direction. That's the orientation that would come from this spin orbit filtering effect I just referred to. Then in the green curve, we're looking at a more unconventional spin current where the flow and the spin direction are in the same direction. So just to remind you, this is not something you get from the spin Hall effect. This is something that's distinctly different. And that is the type of orientation that would arise from the spin-orbit precession effect that I talked about earlier. So you can see that after the scattering off the interface, you get spin currents that are flowing out of the interface plane in both directions, right? And they're not negligible. This is, about 500 to 1,000 inverse ohm inverse centimeters, and this is a little less than 500, but it's, it's appreciable. So I've also plotted this two ways. The solid curves represent the case in which spin-orbit coupling is turned on everywhere. The dashed curves represent the case where I turn off spin-orbit coupling, specifically in the cobalt layer. So if you look at this top, effect, the spin-orbit filtering effect that's going on, you see that more or less these curves look kind of similar, right? Yeah, it's off by a factor of 2 maybe, but you kind of qualitatively get the same behavior. However, there's a drastic difference in the bottom plot when I turn on spin-orbit coupling or turn it off in the cobalt layer. If I turn it off or turn it on, I get a spin current, right, that undergoes dephasing in the ferromagnet like expected, but then it approaches a non-zero value. So there is some bulk spin current that is also occurring in cobalt. But if I turn off spin-orbit coupling in cobalt, I get dephasing to 0, meaning that spin current is essentially killed through incoherent precession. So what's going on here? That essentially tells us that there is a spin current that is also generated in the cobalt layer, in the ferromagnetic layer, that arises from spin-orbit coupling, which can essentially compete with the interface generated current as well. Okay, so then I can calculate the spin torque that's occurring in the ferromagnetic layer from both of these processes, from the spin-orbit filtering effect and from the spin-orbit precession effect. And what we find is that more or less these curves again look the same whether you turn spin-orbit coupling on and off in cobalt. That implies that cobalt isn't doing much and that this is coming from the interfacial contribution, whereas there's a huge difference if I turn on or off spin-orbit coupling in the cobalt layer for this precession effect. So that tells us that the interface is contributing to this process, but that bulk spin current is also contributing as well. Okay, so I've talked about a simple model, I've talked about first principles calculations, and so now I want to talk about what happens in experiment. So here we looked at a ferromagnetic trilayer where this bottom ferromagnetic layer could be cobalt iron boron or permalloy. We have a titanium spacer layer, and then we have a cobalt iron boron out of plane layer. And so we run a current in plane, we apply a magnetic field out of plane to look at the hysteresis loops. And so in a controlled experiment where we don't have this bottom ferromagnetic layer, the hysteresis loops look the same regardless of what direction the current is flowing and regardless of what direction the current is flowing. However, if we add this bottom ferromagnetic layer, and here I'm looking at the cobalt iron boron results, we can actually shift the hysteresis loop from this top layer, depending on what the polarity of the current is here and depending on what the magnetization direction is. So if we stop back and think about this, this is saying that this bottom ferromagnetic layer is influencing a torque on the top ferromagnetic layer via the shifting of this hysteresis loop. And it depends not only on the direction of the current, but the direction of the magnetization of the bottom ferromagnetic layer. So one of the things that could potentially cause this is the stray field from the bottom ferromagnetic layer, but we were able to rule that out using micromagnetic modeling. And so the only other thing that could happen is that a spin current is generated somewhere in the bottom layer, whether it's the interface or the bulk ferromagnetic layer, that flows to the top layer and exerts a torque and thus influences this hysteresis loop. So this is evidence of this spin orbit precession type current that has this orientation right here. So what we then did is we took away the external magnetic field and looked at if we could apply a strong enough charge current so that we could actually flip the top magnetization layer using this spin current. And we were able to do that. And not only that, we were able to show that the polarization depended on what direction the magnetization of the bottom layer is. So this is all strong evidence that there is a spin current that flows out of plane with spin direction out of plane that can exert a torque on these top ferromagnetic layers. So again, why do we care about this? It's not just a novel mechanism of spin orbit torque. It has technological importance because ferromagnetic layers with perpendicular magnetic anisotropy are sought out for magnetic memories for various reasons, including the switching speed. And so anything that can switch a layer with perpendicular magnetic anisotropy is something that's very exciting. And this is one mechanism that can do it. I want to point out that this work was done in 2018. Since then, there's recent work supporting this interpretation by Habino et al. And so you can look at these papers over here to see other mechanisms of measuring the spin current in these ferromagnetic trilayers, or the torque rather, in these ferromagnetic trilayers, and how the bottom layer is influencing the top layer. Okay, so with that, I will go to the final section of my talk, which is looking at the role of the ferromagnetic layer itself. And this is something that was ignored for some time because it was assumed that strong dephasing would essentially kill any spin currents that flow into the ferromagnetic region, and you would get a torque from that. But that the ferromagnetic region itself wasn't really responsible for exerting a torque on itself. We have reason to believe now that that's not necessarily the case. Okay, so to understand the role of the ferromagnetic material itself, or I should say just any magnetic material in a spin-orbit coupled device, let's start with symmetry, right? So symmetry constraints differ between various magnetic materials. So for instance, if you have more symmetry, you have a more constrained spin current. So for instance, a non-magnet has quite a bit of symmetry, and so you get a constrained spin current that actually has to follow the orientation of the spin Hall effect. However, if you have less symmetry, you get a less constrained spin current. So something like a collinear antiferromagnet or a ferromagnet has less symmetry because of the magnetization direction, because you've added these spins that are pointing in some direction that takes away the different symmetry transformations that keep the system preserved. So what are the consequences of this on the spin current that is created in a particular material? So in a non-magnetic material, if I turn on an electric field, I am constrained by symmetry to get a spin current where the flow of the spin given by the wavy line and the direction of the spin given by the blue line is all mutually orthogonal. But as I relax my symmetry, right, by including magnetic order, right, say in a collinear antiferromagnet or in a ferromagnet, for an arbitrary direction of the magnetic order, I'm actually allowed the full spin current. So even if I constrain myself to spins which are flowing perpendicular to the electric field, they can have any spin direction. And again, this is a consequence of the symmetry of the devices. However, it is useful to look at certain high symmetry directions. And what we find is that there are then differences between, say, a ferromagnet and a collinear antiferromagnet. So in a non-magnet, again, we have the spin Hall-like orientation. In a collinear antiferromagnet, if we run a current perpendicular to the nail order, we get a spin Hall type effect, but because this nail order is breaking certain symmetries, we're allowed to have a different spin current in this direction than that direction. So we get kind of an anisotropic spin Hall effect. And if we then go to the ferromagnetic material, we break more symmetries still, and that allows us to have these new spin directions, which I'm showing here. These correspond to the spin-orbit precession-like effects that I talked about earlier. So the point I want you to take away from this is that when you turn on an electric field in a magnetic material, an antiferromagnet or a ferromagnet, you get spin currents where the spin direction is not aligned with the magnetic order. That means that if they flow to the boundaries of that material, they can exert a torque, so that a magnetic material can exert a torque on itself through the spin currents created within the material. Okay, so how does this, come about? Loosely, there's two different mechanisms that researchers talk about when they're studying spin current generation. You can classify those as extrinsic or intrinsic. And it's important to point out that there's not agreement in the community about what these terms actually mean. So I'm going to tell you exactly what I mean in this particular case. So in equilibrium, if we think about the spin current that results just from the carriers in equilibrium, we would calculate that by summing over all of the electronic states with the occupation of carriers times whatever spin current is contributed by each of those carriers. So Q represents the spin current contributed. I represents just label for the electronic state. After I turn on an electric field, I have two things that can happen to linear order. Either I perturb the occupation of carriers or I perturb the spin current, which is carried by those electrons. And so loosely, we're just going to call any change in occupation an extrinsic contribution, and any change in the spin current the carriers actually, carry as an intrinsic contribution. So an example of an extrinsic contribution might be impurity scattering, like the skew scattering I showed you earlier. That's going to not change the spin current, it's just going to change the occupation of carriers by changing what direction they're flowing. However, I can also turn on an electric field and perturb the electronic wave function itself, resulting in a spin current. And we call this an intrinsic contribution. And so I'm going to talk about both contributions in ferromagnets and antiferromagnets. So specifically, what mechanisms am I going to talk about? There's a lot of different ways that this can happen. So I'm just going to focus on two. For the extrinsic contributions, I'm going to look at the case where by turning on an electric field, all I do is I induce a current, as described by the spin-dependent relaxation time approximation. And then I'm just going to look at the spin currents that accompany that charge current. For the intrinsic contributions, I'm going to use the Kubo formula to calculate the perturbation of the wave function that results in a spin current. And if you're familiar with this, this is all intricately tried to the Berry's phase. This is just another way of describing that type of physics. Okay, so let's start with the intrinsic effects in a single layer ferromagnet. So what we did in this paper here is calculate the intrinsic spin currents in transition metal ferromagnets, so iron, nickel, and cobalt. And we found that they have a very simple magnetization dependence. So to remind you what we're doing, ferromagnetic material, turn on an electric field, look at the spin flow perpendicular to the electric field, and calculate all the spin directions that result as we vary the magnetization. So these three curves represent the spin current flowing in the y direction and the different spin directions, so along x, y, and z, as we vary the magnetization direction. Now, as I mentioned before, for the magnetization in an arbitrary direction, all symmetries are broken. So you're allowed every direction of spin current. Yet what we found is actually a very simple spin dependence, very sinusoidal type dependence that could be fit into this formula here, with a term that was independent of the magnetization and a term that was dependent in a very simple way. So one thing to take away from these first principles calculations is that even though ferromagnets allow all of these things, in transition metal ferromagnets, the spin currents you get are actually relatively simple. So looking at that a bit further, I've reproduced here this fitting curve through those, the results from those calculations. As you can see, again, we have this term that doesn't depend on magnetization and a term that does depend on magnetization. The term that doesn't depend on magnetization has the same orientation as the spin Hall effect in non-magnets. So we call this the spin Hall conductivity in ferromagnets, just because it seems analogous to that. However, there's another effect which depends on the magnetization direction, and it seems to have the magnetization dependence as if you were looking at the anomalous Hall effect, so a charged-based Hall effect in ferromagnets, but a spin polarized version of that. So again, for lack of a better name, we called it the spin anomalous Hall effect. But this is misleading in the following way. If we look at the fitting for these parameters, for these different ferromagnetic materials, and we've reproduced this in this table over here, we have the anomalous Hall effect. So this is the charge Hall effect that results in ferromagnets. And then we look at the spin Hall effect and the spin anomalous Hall effect. So here I'm just going to point you to cobalt when the electric field is along one of the high symmetry directions. You can see that the anomalous Hall effect and the spin anomalous Hall effect are related in this way, where the spin anomalous Hall effect has a different sign and is much larger than the anomalous Hall effect. So that cannot result then from a spin polarized version of the charge current that arises. So what this means is that what we're calculating here is actually more general, right? So we can have something that looks like a spin polarized anomalous Hall effect, but in this case, it can have a value that's greater than the polarization times the charge anomalous Hall effect. So again, I've shown you a first principles calculation. Now let's look at an experiment. So this was an experiment trying to see if we can measure the torque that arises from these spin currents that are generated within a ferromagnetic material. So in order to do that, we looked at a single layer material. So this is a 32 nanometer slab of permalloy, which is capped by oxide layers. So what this does is this takes away the heavy metal that can generate a torque from the spin Hall effect, or an interface with strong spin-orbit coupling. So we can just focus on what the ferromagnetic material itself is doing. Now, symmetry dictates that you cannot have a net torque in this material. However, you can have equal and opposite torques at the layer boundaries, right? And so essentially what we looked at was the following. If we have this material, we turn on an electric field, generate a current. If there truly is a spin Hall effect in this ferromagnetic material, that would generate a current which is flowing along this direction, which spins that are perpendicular both to the flow and the electric field. When those spins reach the top layer, the top boundary and the bottom boundary, because they are perpendicular to the magnetic order, they must exert a torque. So it's like the magnetization sort of bends at the layer boundaries. So how do we measure this? We measure it using polar Moog. So this is an optical technique that's used to measure the deviation in M. So I'm not going to go over the experimental details here. I'm just going to say that from that, we can actually extract a lower bound, not an upper bound, but a lower bound of the spin Hall conductivity at about 1,000 inverse ohm inverse centimeters, which is comparable to the spin Hall conductivity in platinum. So what this tells us is that we do have spin current generation in ferromagnets, or at least a torque that is arising, that is equal and opposite at the layer boundaries. So the exciting thing about this is not only does this say ferromagnets can contribute to their own torque, if you can create enough asymmetry in the material, you could change this torque from this torque and actually result in a net torque for the whole system. So I just talked about ferromagnets, but I also promised to talk about antiferromagnets. So again, we have low symmetry in antiferromagnets that can give us a kind of anisotropic spin Hall effect. So what I'm going to talk about is an experiment theory collaboration, which you can read about here in the archive. I'm going to focus only on the theoretical part for now. And so what we were doing was looking at the spin currents that are generated in an antiferromagnetic material, right? So the antiferromagnetic material we looked at was iron rhodium. Here's the crystal structure for iron rhodium. We're going to have the electric field pointing along what we're calling the X direction. And here's the sort of unconventional part. We believe that the nail order in our sample is actually pointing 45 degrees from the electric field, just due to how the system is grown. And so because of that, we can identify two different spin currents that would result in that orientation. A spin current flowing out of plane, so here in the Z direction, that has a spin which is aligned with the nail order and a spin which is transverse to the nail order. Okay, and what we did here using the Kubo formula is calculate the contribution from those two different spin currents. And what we found is while they're not as large as the spin currents that we saw before, they're still 150 inverse ohm centimeters. This is something that can still influence magnetization dynamics in a way that can affect, for instance, switching in a particular material. Okay, so the last topic that I'm going to talk about are extrinsic effects in ferromagnetic materials. And so again, for lack of a better name, we called this sort of phenomena the spin planar Hall effect. And I'll get to why we called it that in a second. So if you recall, when you turn on an electric field in a system, you can perturb the system in a couple ways. The extrinsic mechanism that we talked about involves perturbing the occupation of carriers. So you turn on an electric field, the occupation of carriers changes, and then you sum that change with the eigenstate spin current, and then you get the new spin currents that can result. And how do we model the change in this occupation? We model it using the relaxation type approximation, which is proportional to a phenomenological parameter called the relaxation time times the group velocity. So we can obtain both of these things, the group velocity and the eigenstate spin current, again, from ab initio calculations. So we can get a realistic estimate in this case, in the absence of disorder, for what this sort of spin current would be. Now, I want to emphasize for those of you who are familiar with the different mechanisms in which spin currents arise, that this does not include skew scattering, and this does not include side jump. So this is a mechanism that is actually distinct from those two, which are typically associated with the spin Hall effect, that occurs only in materials with magnetic order. Okay, so here are the results of that calculation. And now I'll tell you a little bit about why we call this the spin planar Hall effect. So what we've done here again, turned on an electric field. This is all theoretical calculations. We then calculate the spin current that forms based on the theoretical mechanism I showed you in the last slide that is flowing perpendicularly to the electric field. And we look at all spin directions of that spin current as we rotate the magnetization, okay? So if you look at the results over here, plotted as I rotate the magnetization from the Z direction to the X direction. First, we calculated the charge current, and that charge current is exactly the charge current you would expect from the so-called planar Hall effect, which is another well-known Hall effect in ferromagnetic materials. So we are capturing part of the physics that gives you the planar Hall effect, right? And now all we're going to do is say, given that same perturbation that creates that charge current, this planar Hall effect, let's just look at the accompanying spin currents that result. And so what we find is one spin current where the spin direction is aligned with the magnetization. So that looks like a spin polarized version of the planar Hall effect. You know, to explain that in more depth, anytime you run a charge current in a ferromagnet, it's spin polarized because of the magnetization. So if you get a charge-based Hall effect, you expect there also to be a spin polarized version of that too. But again, the catch here is that if I look at this curve, it's actually about the same magnitude as the charge current. So this can't be explained as the charge current times the polarization of the ferromagnet. It's not just a spin polarized version of that, it's something more that's allowed by symmetry. If I then look at the spin currents which are perpendicular to the magnetization, you know, we can extract that those spin currents have this sort of magnetization dependence, and you can see that they are non-zero as well. So again, this points to the idea that when you run a current through magnetic materials, you create spin currents where the spin direction is not aligned with the magnetization. And so those can exert torques when they flow to the layer boundaries, and they can contribute to the spin orbit torque that we've been talking about earlier. Okay, so with that, I would like to conclude. The traditional picture of spin orbit torques requires modification. Interfaces generate spin currents via spin orbit scattering at the interface. And that's another effect which leads to, that can contribute to spin torques in the ferromagnetic layer. And both ferromagnets and antiferromagnetic layers, meaning separate layers than the ones that are receiving the torque or that layer itself, generate spin currents with a direction perpendicular to the magnetic order. And I'll just conclude by saying that these novel effects have been measured, or at least there's strong evidence supporting that they exist, and that they can create new functionality in devices. For instance, exerting torques on materials with perpendicular magnetic anisotropy and switching, you know, these perpendicular devices. So with that, I'll thank you for your attention, and I'm happy to answer any questions that you have.
Okay, thanks, Vivek, for this very interesting talk. I think everybody thoroughly enjoyed. We had about 50 audience, and it was more or less same throughout the talk. That just tells that your talk was very exciting and carried out all the people with you. Before we take the questions, I'd like to request all of you to switch on your camera, and Vivek, just stop sharing for a minute. We take a group photo and then we'll come back to your talk again.
Okay.
So please switch on your videos, and I will take some snapshots, screenshots. Okay. Thank you. I'm taking smile. All right, one more. There are a lot of people. A lot of people are not switched on the camera, but I respect their decision. All right, so it's all good, I think. So I request now everyone to switch off your videos. And Vivek, you can again share your screen. And let me see if there are already some raised hands. So, well, there is a question from one of my students. How can we know the spin-orbit coupling of an interface?
Yeah, that's a great question. And we don't have a good answer to that question. So the spin orbit strength at the interface, first of all, how do you quantify that? Theoretically, you can look at band splitting. If you, again, as a theorist, we create our models. So we can put spin orbit coupling by hand. We have that luxury. But in an experiment, we don't, right? The other thing is that just because something has what we think of traditionally low spin orbit coupling in terms of the splitting of the bands, it doesn't mean the resulting effects are going to be small. So I had shown before when we had calculated the interface generated spin currents at a cobalt copper interface. Copper has small spin orbit coupling and cobalt is not that substantial, and yet we saw a big spin current. So the point I'm trying to make is that first of all, we can't really measure the strength. And second of all, even if we could, that strength isn't necessarily telling you how strong these effects are going to be. We need spin orbit coupling, but it's not really a valid comparison, between effects. So this is definitely an outstanding question. Are these things really resulting from the interface? Are they resulting from the bulk? There are methods that can kind of shed light on that, but they're not really satisfactory yet. So it's a good question.
Okay, there are some other questions, but before I forget, I have one question related to the intrinsic spin Hall effect from the ferromagnet. So when you model the iron or cobalt, I believe they are like epitaxial films because you build a lattice. I wonder the crystallinity, does it have any effect? Like if you make epitaxial or polycrystalline or like cobalt iron boron, which is a very famous amorphous ferromagnet. So do you think this intrinsic spin Hall effect will also depend on the crystallinity or it's independent?
Yeah, so, I would expect it definitely to depend on disorder or the crystallinity of the system. Along those lines, we did these calculations and I showed you the, sort of perfect, say epitaxial version of this. But we did look at putting disorder in through a broadening of the imaginary part of the energy. So essentially this gives you an effective relaxation time, right, in your calculation. And what you find is that as you increase that disorder strength, you do have the spin currents reduce in value, like say, they may go to half. I don't know the numbers off the top of my head, but they don't die away. So essentially what that tells us is, yes, disorder does affect these calculations, but it doesn't necessarily, destroy the effect. Now that is only one way of including disorder, right? There are other ways we can include disorder theoretically. Those may have more drastic effects, but I guess the short answer is we don't necessarily know what it is, but I certainly expect it to play a role.
Okay, if you go a few slides back, there was one ab initio calculations between cobalt and copper, where you saw like an enhancement of the spin current around the interface. I'm sorry I missed. So what is exactly happening? Because copper is not a high spin orbit coupling, so it is more intrinsic. But then you are telling that it is getting, I think this one, it is largely getting enhanced near the interface. So what is the reason behind that?
Yeah, so I would maybe say rather than enhanced, it's getting generated at the interface, right? And it's getting generated through scattering of electrons at the interface as they see the spin orbital field. So essentially, it's these mechanisms here, if you can see the animation, where spins that are either unpolarized or majority and minority carriers in the ferromagnet, they scatter off the interface, they see the spin orbit field, they either process or get filtered, and then that's what generates the spin current. So to answer your question about spin orbit coupling strength, and this ties, I think, back to the question before, it's tempting to say that if something has, say smaller spin orbit coupling than another material, you expect half of the effect. But first of all, theoretical calculations tell us that's not necessarily true. As you ramp up spin orbit coupling, there isn't necessarily a linear dependence between the strength of the effect and the spin orbit coupling parameter. And two, you're not really comparing apples to oranges here, right? So if I look at the spin Hall effect in a heavy metal like platinum, where I know the spin orbit coupling is strong because it's a heavy metal, and then I calculate a totally different effect, interface generated spin currents in cobalt and copper, where the spin orbit coupling is weaker, that doesn't necessarily mean that the interface generated spin currents will be weaker than the spin Hall effect in platinum, because those are two different effects that depend on spin orbit coupling in different ways. And so that's why you can see an effect you might think is strong in a material with what you call weak spin-orbit coupling, right? Weak is all relative. It's just relative to another material and another effect you calculated. So it doesn't have to work in that way. Hopefully that made sense. But
okay, I have something to ask, but I can ask you later. There are other questions by like Pranav. You would like to ask, or should I read it?
Hello. Yeah, very nice talk. I was just wondering about this spin anomalous Hall effect and spin planar Hall effect. These are bulk effect, right? This is bulk of the ferromagnet, right? If I understood correctly.
Yeah, that's right. So these are effects that occur deep within the ferromagnetic material, and actually they cannot exert torques again by symmetry arguments. Even if the spin direction is not aligned with magnetization in the bulk, they can only exert torques when they flow to the interface of the layer boundaries where inversion symmetry is broken. But yeah, what I'm describing is a bulk effect.
How do one measure this experimentally? Because you measure a Hall effect, you have normal anomalous Hall effect or planar Hall effect. How do one distinguish it from the?
Right. So that's what we did in this particular experiment. So, you know, my talk was shy of a lot of these experimental details, but effectively what we did was use polar moke to measure the deviation in the magnetic field. So in other words, if you're not familiar with magneto-optical Kerr effect, you can send light into this material that will scatter, and based on analyzing the scattered light, you can tell something about the magnetization of the target material. And so because this sample was so thick, it was about 32 nanometers, and I don't exactly remember the light penetration depth, I think maybe it was on the order of 10 nanometers or something. You can basically probe the top and bottom parts of this sample with light and change the distance from the source and get a curve of, you know, what the net magnetization looks like. And, you know, essentially by deconvolving that, you can then look at, you know, what the magnetization direction is in the top layer and the bottom layer. So this is an optical experiment that was used to probe the deviation in the magnetization at the boundaries. And that deviation has to come from a torque. We are simply postulating that it's coming from the spin current, and then as a result getting this value. But it's possible that it could come from other sources too. So you can't directly measure the spin current, right? You can't do that really with any method anybody has. You can only measure the torque. And again, we can just say that if there was a spin current that was generated in this material, here's what its, what its strength would have to be to create that torque at the boundaries. Does that answer your question?
Yeah, more or less. Yeah, thank you. Just one more question I had was about the interfacial torque that you had predicted. So this SpinOrbit filtering and spin-orbit precision current. So this is going to have a polarization, spin polarization, which is either Z or Y. So Y is the standard RASPA kind of polarization, right? Is that Raspa-Eisenstein?
Yeah, so this SpinOrbit filtering effect has a polarization in the Y direction. Again, assuming the electric field's along X and the interface normal is Z, then Y direction is the direction of the spin Hall spins and the Raspa-Eisenstein spin accumulation. So yes, it's in the same direction. So again, this is very difficult experimentally to separate from those other effects. But it does have a different dependence on disorder, on the conductivities of the materials. Even how you model it in the drift diffusion equations, it's different if you consider the interface creating a spin current versus a spin accumulation diffusing from the interface. So while it's difficult to disentangle, it does behave differently and has a different dependence on material parameters than the Raspa-Eisenstein effect. The spinor, sorry, go ahead.
Yeah, thank you. That's good to know. I didn't know that. Yeah. Thank you very much.
Yeah, thank you. Are there any questions from anybody else? Oh, there were Chandrasekhar, please.
Thanks, Professor Amin. this wonderful talk. I would like to just know that the thermolite that you have used 32 nanometer, right?
Sorry, can you repeat that again?
Yeah. So in the thermolite work, the bulk thermolite 32 nanometer one, which you have just shown, could you please go to that?
Yes. Here it is.
Chandra, you may have to speak a little bit louder. Your voice is not very clear.
Okay, Shubhankar bhai.
And now it is very good, please.
Yeah. So my question is that have you capped with any other layer, or is it only permalloy?
Oh,
in the experiment.
Right. So yeah, in the experiment we looked at a few material systems, but one of the interesting things is that within permalloy we looked at different capping layers, and that was also one of the ways in which we, at least that's evidence that points towards an internal spin current generation mechanism rather than something that happens at the interface, because the torque strength by and large was not affected by what materials we used as the capping layer. Right.
Okay, great. Yeah. And then I was just thinking that because permalloy may get oxidized, so you might have kept some kind of aluminum or something just to see that if that has any effect. But you are saying that it's not there. And what are the kind of magnitudes of the currents that we are looking at here?
In terms of the charge currents?
Yeah, charge currents. Yeah, you apply voltage, right? So what is the magnitude?
Right. So I don't remember off the top of my head, but I could certainly look that up.
No worries. I can go through that. And I mean, okay, this is a very stupid question, maybe. Kindly bear with me. But if at all there is a torque, and then yeah, of course there is a torque, and then how much would be the kind of the rotation that can happen from polar mode? Can we find out?
Okay, so if you're asking what is the angle at which the magnetization deviates from this direction along the
from in plane to out of plane, that's what I want to know. Yeah,
right. So again, I also don't remember what the deviation angle was, but from that deviation angle and a simple sort of micromagnetic model, we can extract a spin current value of about 1,000 inverse centimeters. But as far as the deviation is concerned, I'm sorry I can't give you these details. It's just, and I don't remember them off the top of my head.
Yeah,
they should be in the paper. But it was something that was within, it was obviously that was within the sensitivity of the polar mode measurement.
Great. Yeah. Thank you, Professor Amin.
Thank you, Chandra. So any questions by anybody else? One last one, if there is any. Okay, so I don't see that. Vivek, can you please stop sharing? I like to share my screen. We would like to present a small token of appreciation. Yeah, so very good. Let me share my screen. Please bear just for 10 seconds. Okay. Do you see my screen, Vivek? All right. I mean, we are not meeting in person. This is a digital plaque, a small token of appreciation from our team. I will read it for you. W2S seminar, webinar series on spintronics. Mysore, Bhubaneswar, India. Takes pleasure in presenting this plaque to Professor Vivek Amin from Indiana University, Purdue University, Indianapolis, US, in recognition and appreciation for being a very valuable speaker to give a lecture on anatomy of SpinOrbit Torque. So on behalf of everyone, I like to thank you for your excellent talk. It was really a pleasure in interacting and listening to you. I hope one day you can come to Mysore and we can meet in person here, or maybe the States or anywhere else. So until then, so thank you so much for your talk and your time, Vivek. And thank you all, and see you next week. Probably the time will be different. I think it will be Stefan Bonetti from Italy. So it will be 3 p.m. Indian time, but nevertheless we'll meet. And thank you so much, Vivek. Take care.
Thank you. Thank you for having me.
Thank you so much. Yeah, see you. Bye.
Bye.